Good evening to one and all. Today we are going to discuss loss of illumination here. And what's that loss of illumination? We already started the part there. And we are having to know some two concepts here. One thing is cause, another one is effect. Cause is nothing but here, light. Effect is nothing but illumination. I'd like to know that illumination is represented with the letter E only there. It's not an issue. I'd like to go for the part of what are the different laws of illumination. Let's start our session. Yeah, in order to have this explanation of illumination laws, you have to know some basic things here. Phi is nothing but luminous flux, and unit for this particular luminous flux here is lumens. I is nothing but luminous intensity here. I is nothing but luminous intensity. It's a flux per solid angle. Omega is nothing but, it's obviously solid angle. What's that solid angle is nothing but, it's an area to the part of square of the radius, omega. How much area divided by radius square. And omega is will have some units here as steradians. It's obviously 4 pi. And also we have to insist some more definitions here. Just observe. Yeah, we all know that lumen, and we can have some definition in the previous slide. What's the definition here as this one? I is equal to phi by solid angle. From that, can you elaborate the thing of phi is equal to I into omega? Remember that one. I may use it there. Candle power is nothing but a total luminous flux lines emitted by the source in the unit solid angle. That it is flux by solid angle. Candle power. Yeah. This I is nothing but candle power unit for the part of intensity. And also we have to remember illumination. Flux per area. Flux phi is nothing but flux per area. I can write that phi is equal to I into that particular omega. Yeah, here don't neglect the thing. I is nothing but intensity. Na? The unit for the part of intensity here is candle power. That's the only thing they have written here. Remember all those definitions, then we go further. Yeah, in order to have this particular illumination on the surface, mainly depends upon three factors there. The illumination on the surface, yeah, when I would like to have some illumination in the sense light, it can liberate it like this now. They have some three factors like this. The first and foremost thing here is it mainly depends upon intensity wise, I, and also the distance between source to the part of surface. The light will split like this now. This one is the source and this one is the surface you have to ventilate here. And how much distance it covered, that's the main intention of this particular illumination. And the third point here is the direction of rays of light also plays a crucial role. These are the three main factors. It mainly depends upon the part of which thing here, illumination on the surface. Yeah, in order to have this clear-cut explanation wise, I'd like to go for the part of laws. Those are the two laws here. One thing is nothing but inverse square law, first law there. Another one here is Lambert's cosine law. Yeah, the first and foremost thing here is inverse square law. We already explained the part inverse square is nothing but that it is 1 upon is inversely related to square law, that it is square of the distance like this. That's it. Yeah, illumination on a surface, that it is E, is inversely related to the part of square of the distance between the surface and the point source. Yeah, let it be we are having some source and this one is the plane surface like this. How much distance it has to cover, that it is inversely related. That's the first law. Let it be for the clear explanation wise, I can choose some like this, different areas like this. This one is the first area, area number 1. This one is the second area, some larger area there. And the third one like this, different areas. Each area will have some A1, A2, A3. And this what's this angle is nothing but solid angle omega. Yeah, we all remember one thing, that solid angle is nothing but if you would like to consider one area part. Can you remember that area? This one is the area. And what's this angle? Maybe call it as omega. This one here, omega. And what's that distance here is r. And what's that solid angle formula? Omega is equal to area divided by square of the distance. This one is the thing. If I'd like to consider the source here is S. For the first one, the distance here is d, and for the second one, distance here is 2d. Just replace this r with the help of some d. That's enough. And the third one, 3d distance. For the clear explanation wise, for the area A1, I have some solid angle. Omega is equal to what's this one? A by square of the distance, d square. Yeah, luminous flux reaching the surface area A1 is equal to, we have some formula now. From this particular formula, can you write what's that luminous flux phi is equal to? That intensity I into omega. This one is the thing. Yeah, we can have some luminous flux phi. Luminous flux phi is equal to intensity into solid angle omega. I into omega. I into what's that omega? You can write A by d square. And what we know some illumination formula E is equal to flux by area. Flux by area. What's the flux value here? I into A1 divided by d square into the part of 1 upon A1. A1 cancel out, and this one is I divided by d square E. This one is the first. Similarly, in a similar fashion, can you go for the part of second area wise here? How much distance it have covered right now? 2d. Replace this one as 2d square. Everything is common. Second area now, this one becomes A2 and this one becomes A2. This one. First one is E1 is equal to I upon d square. This one is the first area wise consider. Second E2 on the surface area A2. That it is I upon 2d square. Similarly, for the part of third one, nothing is there. Only remember one thing, that illumination is inversely proportional to the part of square of the distance. 1 upon, make it this one as I. That's enough. This one is our first law. I stands for intensity. We can observe E1 is 2, E2 is 2, E3, I by d square, I by 2d square. All this when the distance is changing, it's inversely related. Yeah, illumination on any surface is inversely related proportional to the part of square of the distance between the part of which thing? Source to the part of surface. This one is a source and this one is a surface wise. That's it. This one is a laws of illumination, first law, that to inverse square law. Try to go for the part of second law. Same thing, nothing new, but try to remember first law is for the part of plane surface, whereas this one is on at an inclined plane. Yeah, this law states that illumination at any point on a surface is directly related to the part of which thing? Cosine of the angle between the part of two things, normal to the part of flux line. I'd like to draw some normal. Normal in the sense it's a perpendicular. Yeah. While discussing this Lambert's cosine law, just remember we are having some source. I would like to have some light rays will travel like this, incident at a point P. Observe. Try to draw some normal here, perpendicular, and how much angle it tilting like this here is theta. And in order to elaborate the part of this one also becomes theta there. Observe this one triangle here. I'd like to shade this triangle. Yeah, from this triangle, h is the distance from the part of source to the part of which thing here? Plane surface, h. This d is nothing but it's a distance between the part of source to the part of point of rays traveled at an inclined plane. This one. From this plane, can I identify from this right angle triangle, what's the value of cos theta here? Adjacent side h divided by hypotenuse d. That's it. Remember that thing. And the Lambert's cosine law will have only one thing, that illumination is directly related to the part of same thing. What's our first law? I by d square. But try to insert one thing here, cos theta. I know this cos theta value now. What's that cos theta value? H by d. Substitute here. From that, what's the value of d? H upon cos theta. Substitute the specific one in this one. I by h square cos square theta like this. And we can finalize I is equal to E is equal to I by h square cos cube theta. Yeah, remember d is nothing but distance between the source and the surface in meters. H is nothing but height from the source, from the surface in meters. And what's that I is nothing but luminous intensity, which is measured in candela. From this particular, this one is equation 3 like this. This one is our cosine cubes law, or else Lambert's cosine law. This law states that illumination at any point on the surface will depend upon the part of which thing cube of the cosine. That's the main thing. And finally, we can finalize one thing here. Only two laws. Illumination E is equal to I upon d square. What's our second law? Same thing. I upon d square. But try to remember I have to insert one cos theta. Then we can finalize this one as I upon h square cos cube theta. That's it. This one is a cosine law, Lambert's, and whereas this one is a inverse square law. That's it. These two laws is for the part of which thing illumination. E is nothing but illumination. Yeah. And try to remember one thing, inverse square law is only applicable for the surfaces if the surface is normal to the flux lines. And whereas Lambert's cosine law is applicable for the surfaces if the surface is inclined at an angle of theta. Remember that thing. If there is any inclination upon the part of angle theta, that one is for the Lambert's law. If it is a plane surface, we can call it as inverse square law. That's it. Remember these two laws plays a crucial role. E equal to I upon d square. I stands for intensity, d stands for distance. Yeah, these two laws plays a crucial role in this illumination engineering concept wise. Thank you for watching here. If you like my videos, please subscribe to my channel. This one is our channel name. Yeah. Thank you.